Hi students, welcome back to geology. We are now going to elaborate on the separate mineral groups. So how do we look at minerals and separate them into different groupings? Okay, so as we go through this video, I want you to think about how minerals are classified and what are important groups to know. So as we go through this, hopefully that starts to make sense. So there's two main mineral groups. They're kind of the big umbrellas. There's silicate minerals and there's non-silicate minerals. Silicate minerals contain a silicon oxygen tetrahedron. So these are the two most abundant elements in Earth's crust, making silicate minerals the most abundant minerals on Earth. Okay, and then the non-silicate minerals do not contain oxygen and silicon, and then each of those are divided into some subgroups. So, for example, the silicate minerals contain olivine group, pyroxene group, amphibole group, micas, feldspars, and quartz. And then the non-silicates, we have carbonates, halides, oxides, sulfides, sulfates, and native elements. All right, so getting into the silicate minerals specifically, they are built around a molecular ion called a silicon oxygen tetrahedron, which is that thing that's kind of spinning there for you. So they have four sides, and it looks kind of like a pyramid. So four sides, including the base, three on the surface there, and then there are 4 points that connect all of those pieces. Silicate minerals are the largest group of minerals on Earth, and they comprise most of the Earth's mantle and crust. The silicon oxygen tetrahedron consists of a single silicon atom at the center, and then 4 oxygen atoms around that silicon atom, and that forms that tetrahedron. So the pink balls there, the balls are the oxygen atoms, and then right there in the center, you can kind of see a little bit of a dark spot between the pink balls. That is the silicon atom. So here's a chart on the left that has olivine at the top. You can see that the silicate structure is fairly simple. It's a simple tetrahedra when we're looking at olivine. Olivine crystallizes really quickly out of a magma at a really hot state. So when the lava or the magma is really hot, that's generally when we're going to see the crystallization of olivine. We go all the way down to the bottom, which would be the opposite end of olivine is quartz. And quartz, while it has a simple chemical formula, it's only silicon oxygen, it has a 3-dimensional network. So its crystalline lattice, which is all of those red little beads there, is really complex. And that creates this really complex crystal that is quartz. Quartz takes a long time to crystallize. It is the last to crystallize out of a magma or lava, and they usually end up fairly large. So the longer it takes for a crystal to crystallize, the larger it will grow. Our non-silicate minerals, again, do not contain the silicon oxygen tetrahedra, and they are separated into the various groups here based on what they contain. So, for example, the carbonates contain carbon and oxygen. The sulfides will contain sulfur, and your native elements, which are at the bottom there, will contain just one single element. So gold just has gold in it. Graphite only has carbon in it, so on and so forth. So we'll go through each of those and show you some examples because there's no pictures here, but I have some pictures of examples of minerals in each grouping. So carbonates contain carbon. 2 of the most common that we see are dolomite and calcite there. They look very similar, but there are a few differences between them. And when we get to physical properties, that will kind of start to make sense. Right now, we're just looking at groups. Halides contain chlorine, fluoride, and bromine. So halite and fluorite are 2 examples here. Oxides contain oxygen, and these 2 actually also contain metals. Different metals between the 2, but we have hematite on the right-hand side and magnetite on the left. Magnetite has 2 paper clips on it because it is magnetic, so it will attract magnets and other things that are metal. Sulfides contain sulfur, so 2 examples here are galena on the left and pyrite on the right. Pyrite is our fool's gold. Oftentimes it's referred to as fool's gold. It looks like gold, but it has no other properties and it's not made up of gold to the actual gold. And then sulfates are made up of sulfur and oxygen. An example here is gypsum. One of the really unique things about gypsum is it's not very strong. So its hardness, which we'll look at physical properties in a little bit, is really weak. So if you look at the sample that's there, you can see all kinds of scratches on it. It's because the mineral itself is not very robust against things that it comes in contact with. And then we have our native single elements. So these are things that are made up of a single element bonded together, different atoms to form the mineral. So silver is made up of silver, gold is made of gold, graphite is made of copper, sulfur is made of sulfur, and diamond is also made of carbon. I said graphite was copper. Graphite is carbon. So both graphite and diamond are made of carbon. One has just experienced way more pressure than the other. And graphite is what you'd find in like your pencil lead. All right, so some final thoughts. There are two main mineral groups, right? Our silicates contain that silicon oxygen tetrahedron, and our non-silicates do not contain silicon oxygen. In your notes, I want you to write down which mineral group you think halite belongs to, silicate or non-silicate. All right, I'll see you guys in the next video. Bye.